I welcome everyone to this video. I am Mr. Ish. We're looking here at an exercise in resonance structures using benzoate. What is benzoate? It's your anion derived from deprotonation of benzoic acid. Benzoic acid, let's look at it. You have COOH attached to a benzene ring. If you were to deprotonate it, what will you have? You will have exactly what we have here as our title, benzoate. This is what it is, and then you have your proton. This right here is a good acid. It's a relatively strong organic acid because the benzene can come into play by means of resonance and stabilize this structure. If you can form this relatively easy and you can stabilize it, then you will see this develop and it will be a relatively good organic acid, a strong organic acid. But let's focus here at benzoate. You know, when you're looking at the carboxylate group, you're looking here at this. When you're looking at the carboxylate anion, you're looking at this. This is what it is. Look here at the electrons which are involved. This is exactly what we're talking about. We're looking at the resonance involving this structure, and let's look at it. Let's look here at the resonance structures involving the benzoate. This carboxylate group over here, compound, if you can stabilize it, then the original benzoic acid will deprotonate to generate this. If this is stabilized by means of resonance, that proton will be seen, and you can say benzoic acid is a good or a strong organic acid. What's the first resonance structure that comes to mind? You can shuffle electrons around using the carboxyl functional group. What would that be? Let's look at it. I'm looking at something which looks like this. I have a shuffling going on over here. You'll have two electrons come over here and then form a double bond. These two electrons will come over here and you'll shuffle the electrons around. You'll look at something which comes like this, and here can be your very first resonance structure. Keep in mind at all times the charge over here for benzoate should be a -1. You have to maintain that. I have a -1 here, I have a -1 here, and it looks good. The first resonance structure involved nothing more than shuffling of these electrons. What's another resonance structure? Let me show you. Look what I have over here. I'm going to shuffle this one electron right over here. I'll break the double into a singlet and look what develops. I have this staying as is, but now I'm looking at this as well. And then I have my benzene group, my benzene compound. The carbon has lost its valence from 4 to 3, so it has a positive. It's a carbocation, but you have two negatives, but look at the net charge, it's still -1. -2 plus 1 is a -1, but that is also a resonance structure. What do you think else can come into play? We can start involving the benzene compound. How can we do that? These two electrons, you know, a line is always equal to 2 electrons. Those 2 electrons can shuffle over here and complete the valence of that carbon. And how would that play out? Let me show you. You're looking here at a double bond formed with that carbon. You still have your oxygen, which looks like this. Both of your oxygens will have a negative, and the carbocation will end up on the benzene compound. It will look something like this. This is exactly what we have. I have a carbocation here and my double bond here, double bond here. Look at the charge on this compound. It's still a -1. The -1 will be maintained no matter what. Now you can shuffle electrons over here. You will see the shuffling come over here. The double bond will end up here and the carbocation will end up on the other vertex of this benzene. And it looks something like this. Everything else will stay exactly as is. The fact that you have all these resonance structures will make it possible for the benzoate to be stabilized through resonance and make the original compound, your benzoic acid, a strong organic acid. Now what you have done is shuffle the double bond over here. You have a carbocation here and you have this. You can do one more shuffling, which will be this over here, and you'll end up with the carbocation over here, and that will close everything out. This is everything else as is, as you see it. Nothing else is changing. The only things occurring now are entirely on the benzene compound, on the benzene ring. And my carbocation has ended up over here. If you look at this compound, they're technically the same if you just flip them around, but it's still two different resonance structures. You have a double bond here and you have a double bond here, and we will close it out with this. Your resonance structures are complete, but in each case you'll see that the charge is always -1. The net charge is -1. I have 1, 2, 3, 4, 5, 6 resonance structures. and all of these end up stabilizing the benzoate because they're all different possibilities that come into play to handle that original negative charge. What are the most stable resonance structures from these six? Obviously these two, because you have the fewest number of charges involved. You only have a minus, a single minus. These are less stable because now you're bringing in multiple charges, minus, minus, positive, minus, minus, positive, minus, minus, positive, and minus, minus, and a positive. But they're still feasible resonance structures. There's 6 of them total, and it helps stabilize this compound. The carboxylate functionality is stabilized. The original benzoic acid ends up being a strong organic acid, a good organic acid. And that right there is the end of this video. Thank you for watching.